for coming back. So, as you can remember from the last video, we determined the areas using simple geometry to determine what these areas are. So, in this video we're going to define a few items that will become essential to our understanding of integral calculus. And then we're going to actually delve into integral calculus in the next video, where we're going to be introducing antiderivatives and the fundamental theorem of calculus. Okay, so let's start with this function. Well, actually, let's first define a few terms. So we have two functions, big F and little f of x. So right now this is just the hand-waving argument, and we're going to see this later on. But if big F prime of x, which means the derivative of the big F, is equal to little f of x, then f of x, big F, is the antiderivative of little f of x. Pretty straightforward. Because f of x is, little f of x is the derivative of f of x. So if we have a derivative, we must have an antiderivative. But right now we don't know any implications of the use of these antiderivatives. So what we're going to be doing is developing the possible uses of these techniques. So first let's start off with something simple. And we can rewrite these for bookkeeping purposes, such that f of x is our y value. Let's just write up here, f of x can be defined as y. Okay, so let's box these. And let's go piece by piece. Okay, so we first start off with f of x is equal to 3. Okay, so f of x is equal to 3. So we want to find some antiderivative of x. So we start off with looking at f of x is equal to 3. So we want to try to think of some function where 3 is the derivative of that function. And we can simply just come up with 3x, because the derivative of 3x is 3. Okay, so we can kind of see something. So let's go back to our expression of area over here. Area is equal to length times width. The width of a rectangle, in this case, remains constant. Well, width of a rectangle remains constant. Not just in this case, but we have our length will be 1, 2, 3, 4 times width is 3. The width pops up also up here, and the width pops up over here. The length, we can see 4 minus 0 is our x values, which are right here. So if we were to find if we were to integrate, if we were to find the antiderivative and find the area of this function, find the area of this function, what we do is find the antiderivative and find the integral under certain values. So, for example, in this case, if we would find the area under from x is equal to 0 to x is equal to 4. So is equal to 3. 4 minus 0 is equal to 12. So the way that we can write this (0 to 4). Don't worry about this for now. This is just for bookkeeping purposes. We'll go into more of what this means in another video. Okay, so we have proven that the antiderivative works for this function. Now let's look at this function. So we have f of x is equal to x. So the a function where the derivative is equal to x. Let's look back a little bit to derivatives. So derivative of x squared is equal to 2x. So let's say we divide by 2. So the derivative of x squared over 2 is equal to x. So we can rewrite this as x squared over 2 is our function. So let's kind of go from here to our area expression. So the area is equal to 1/2 base times height. That's the definition of the area under a triangle. So let's just say, for our purposes right now, that these two are equal. Base times height. We're going to later show that this is in fact true. So let's just rewrite this as 1/2 x squared is equal to 1/2 base times height. So get rid of these 1/2s. X squared is equal to base times height. Now we have f of x is equal to x. So y is equal to x. Base is equal to height. So base is equal to height, so we can replace base with height or height with base. So let's just write this out. X squared is equal to, and just to keep things nice, let's keep consistent with calling x base. X squared is equal to base squared. X is equal to base. So we have just proven that this statement is in fact true. So let's go one step further and actually plug in values. So we have x is equal to 4. So we have x is equal to 4. 4 squared is 16, divided by 2 is 8. So therefore, this is true. Now our final example. F of x is equal to x plus 1. X is equal to -1. 2x is equal to 4. So let's just keep this in mind. we have already defined x. The integral of x is equal to x squared over 2. We've already defined that. Now let's just redefine of 1, the integral of 1. So a function where the derivative of that function is 1 is simply just x, because if you take the derivative of x, you get 1. So we have x squared plus x squared over 2 plus x. So let's rewrite this as x times x, 1/2 x plus 1. So let's just set this aside for now. Okay, so let's look at this. So x squared over 2 plus x from x is equal to -1 to x is equal to 4. So let's just do that out. So here and here, we basically took the value of our integral and subtracted f of x2 minus f of x1, and that became our integral. And this is what is going to be defined as our fundamental theorem of calculus, but we haven't actually formally proven it yet. So we're just going to once again do a hand-waving argument, and in the next video I'm going to actually prove the fundamental theorem of calculus. So x squared over 2 plus x. So we have x equals 4. So let's start off with x equals 4. So 4 squared over 2 plus 4 minus x equals -1. -1 squared over 2 plus -1. So we have 4 squared is 16 divided by 2 is 8 plus 4 minus 1/2 plus minus 1. Okay, now let's leave this here for now. 8 plus 4 is 12, plus 1 is 13, minus 1/2 is 12.5. So we've already established that this is true, but let's look at this expression right here and compare it to what we have over here. So we can have, let's separate this into 3 parts. So we have one triangle, we have one small triangle, one rectangle, and one larger triangle. So here, this little triangle, the area of that is 1/2 base, which is 1, times height, which is 1. So that is equal to 1/2. The area of this is length, which is 1, 2, 3, 4, times width, which is 1, is equal to 4. The area of this right here, if we were to move this down, it would be y is equal to x. if we were to move this down one. So let's essentially move our coordinate system up one. We can already do this. We can do this because we have already taken care of all these areas underneath this larger triangle. So we can redefine this as y is equal to x. So the area of this larger triangle is A equals 1/2 of base, which is 4, and height, which is 4. So 1/2 times 4 squared. So we have accounted for the 4 squared over 2. We've accounted for the 4. And we have accounted for the 1/2. However, here we're subtracting. So we have to add some value here to make sure that we're actually adding this area. So we're actually going to be adding -1. We're going to be subtracting 1, so that in effect we're going to be doing 1/2 minus 1 is equal to -1/2. So we're doing minus -1/2. So we're going to be actually adding 1/2, which is the addition of this small triangle right here. So that's basically what we're doing when we're doing this. So let's kind of recap and look at x times 1/2 x plus 1. So the 1/2 x kind of talks about both of these triangles. And then the x is really just talking about that triangle. Well, that rectangle, sorry. So we have seen 3 examples as to why this statement is true. Why we have this, and why we can use this as the determination of the area. Now, obviously, we haven't proven this for all of them, but we will later on see that this is, in fact, a technique that we can use for integration. So, thank you for coming back and watching this video. I look forward to seeing you guys back in the future. Thank you very much.